Okay, so now that we have these asymptotic notations, big O, omega, and theta, now we can use these kind of notations and their definitions to put upper bounds, for example, on the running time of functions, and use these to give us a good idea of how the algorithm is going to behave. When we use an upper bound, we are going to say that the algorithm is not going to get worse than this, or the running time is not going to get worse than this. When we put a lower bound, we are basically saying this is the best the algorithm can do. And usually, the algorithms do not necessarily have even to achieve these running time. So if I put a lower bound of 2 to the n on an algorithm, it doesn't mean that there are instances going to reach 2 to the n. It might be that for every instance of the input is going to be doing much more than 2 to the n. But still, that makes 2 to the n, doesn't violate the fact that 2 to the n is a lower bound. Now, of course, one of the issues that we have to make sure, or to make certain that everyone understands, is that when we put an upper bound or lower bound, if all I'm saying is that give me a lower bound on the running time of an algorithm, of course, one can say 0. Every algorithm is going to take more than 0 seconds, right? Or it's going to perform more than 0 operations. Now, that is not an interesting lower bound. Even though we are saying we want lower bounds and upper bounds, we are often implicitly asking for the tightest possible, okay? For the tightest running time possible. And let's now go back to one of these, which we are going to be using most of the time in this course, which is the big O notation. And just a reminder that we say that f of n is O of g of n if there exist two constants such that f of n is smaller than c times g of n for every n greater than n0. Now let's use this definition and try to establish, for example, some upper bound on some functions. And I will take as an example f of n equal 1000 plus 17n plus 2n squared. And I want to show, as I said before when we were talking about the growth of functions, that we can ignore the lower terms and we can ignore multiplicative constant factors. I can ignore the 2, 17, n, 1000, and so on, and just say that this is going to grow on the order of n squared. Where does that come from? Or am I just doing some sort of tricks? If we come actually now and understand the definition of big O, we will see that, in fact, f of n is O of g of n, where g of n is n squared. How do I get that f of n is O of g of n in this case? We have to go back to the definition. Definition says that to claim that f of n is O of g of n, I have to find two constants, c greater than 0, n0 greater than or equal to 0, such that this is going to be bounded from above by c times n0, c times n squared for every n greater than or equal to n0. Now, we can guess some of these numbers, but also we can go about it a bit more systematically. Remember that I'm interested in finding f of n is smaller than or equal to something, right? So the way I would do it is that f of n is 1000 plus 17n plus 2n squared. Now I want it to be smaller than something, right? What is it smaller than? Of course, it is smaller than 2 to the n for many cases and so on. But since I am going after n squared, I have to keep n squared in mind, right? If I want to establish something that is O of n squared, I have to keep n squared in mind, and I have to get to something that looks like n squared. I can say that 1000 is smaller than or equal to 1000 n squared. If you take a number and you now multiply it by a positive number, of course this is smaller than or equal to this, right? 1000 is smaller than or equal to 1000 n squared, except if n equals 0, right? If n equals 0, 1000 is not smaller than or equal to 1000 times n squared. If n is 1, 1000 is smaller than or equal to 1000 n squared. If n is 2, this is where this starts growing faster now. 1,000 is much smaller than 1,000 times 4, and so on. So for this to hold, I have to start now putting condition that n has to be greater than or equal to 1. Okay? For me to make this jump that 1,000 is smaller than or equal to 1,000 squared, I have to have this assumption that n is greater than or equal to 1. So this is smaller than this, plus 17n. 17n also is smaller than 17n squared. Okay? Again, 17n is smaller than 17n squared because we have n squared is larger than n, and we can make this assumption here. Okay? In this case, even if n is 0, 17 is smaller than or equal to 17 times n squared. Okay? So we don't have to modify this condition. This is still going to hold. I cannot lower it to 0 because it's going to violate this one. Plus, 2n squared is smaller than or equal to 2n squared. Okay? Now, you might be asking now, but also 1,000 is smaller than or equal to 1,000n. Or you might be asking, but 1,000 is also smaller than or equal to 1,000n to the 5th, which is true for this condition. Why did I choose n squared? Again, keep in mind that I'm trying to establish it as O of n squared. So I would like to see n squared here, because once I see n squared here, now this is a term that's easy for me to manipulate, because now I can add these numbers here and say 1,000 plus 17 plus 2 is 1,019 n squared. Right? So now I have this function that is guaranteed to be smaller than or equal to 1,019 n squared for every n greater than or equal to 1. Again, I can basically say that 1,000 plus 17n plus 2n squared is smaller than or equal to 1,019 n squared for every n greater than or equal to 1. Okay? Now, when I look at something like this, and look at this kind of definition, now you can start seeing some sort of correspondence. This is f of n. This is g of n. So what do I have here? F of n, now I have f of n is smaller than 1,019 times g of n for every n greater than 1. The last thing I need to do is try to find c and n0. But they actually jump at you once you look at it like this. Because if you look at this, just call this c, call this n0. We have to make sure that this, if I call them c and n0, that they satisfy the properties of definition. Definition says that c has to be greater than 0. It is greater than 0. For example, if doing this exercise I got to minus 3 here, I couldn't call minus 3c because c has to be greater than 0. I called this n0. n0 has to be greater than or equal to 0. 1 is greater than or equal to 0. So I am done. Okay? I am done. I showed that I can find a c, I can find an n0, such that this function is smaller than or equal to c times n squared for every n greater than or equal to n0. The c is 1,019, the n0 equal 1. So this is what I meant in the beginning when I said that we will be doing rigorous mathematical reasoning rather than proving. I'm not saying that this is a full proof that this is true, but we can argue, or this is not the technique for proving formally that f of n is g of n, and it might not work for many cases, but it's easy for me to reason about how this is smaller than c times this by using this kind of technique. Okay? So here, I just showed a specific value of c, a specific value of c of n0, such that I can bound f of n from above by c times n squared for every value of n greater than or equal to 1. And this is how we would basically do this kind of exercise. Now, if this was omega, for example, if I said f of n is omega of n squared, we can do a similar exercise, but then we shouldn't be focusing on showing it is smaller than or equal to something else. We should be focusing on greater than or equal to something else. Okay? And the last thing I want to say is that if you want to show a function f is theta of g of n, and you have showed that the function f is O of g of n, and the function f is omega of g of n, in fact, you are done. Because it's easy to see that if f of n is big O of g of n, and f of n is omega of g of n, you can conclude from these two that f of n is theta of g of n. Okay? In fact, you can go also this way. If you prove that f of n is theta of g of n, you have in fact proved that f of n is O of g of n, and at the same time, f of n is omega of g of n.